Yeah, hi. My name is Tamim Asfour. I am from the Karlsruhe Institute of Technology, and I'm happy to be part of this workshop dealing with an important topic for robotics, cognitive architectures for robotics. And in this presentation, I'm going to describe briefly our work towards the development of a robot cognitive architecture and give some examples of the architecture we have been using in our work in the last 2 decades. So my work is actually focused on humanoid robotics, in particular, actually, the engineering of these robots, so building these robots which should act in human-centered environments to support humans in daily life by grasping, manipulating objects, handing over objects, with the goal that these robots should also be able to learn from human observation and from experience, and to act in and interact with interact and communicate with humans using natural language in a natural way. And these are some of the abilities of our robots in the kitchen, grasping and manipulating daily objects, but also tools, execute complex tasks like loading the dishwasher, and adapt skills to different tasks and different situations based on sensory feedback. They are also able to learn from human observation and interaction with human, and to interact, as I mentioned, with humans in natural language. And in particular, recently, they are able to recognize the need of help of a human and to provide this help in a proactive way. You see here 2 examples of a complex task in the kitchen environment where the robot is helping a human to prepare dinner for 2 people. And in the other video, you see the robot acting as a collaborative partner together with the human technician in the context of repair and maintenance tasks in industrial environments. So what's behind that? Of course, an architecture, and briefly, it's a hybrid architecture in the sense that it combines experience-based learning and generative knowledge extension. And what I believe is key and important when thinking about putting things together, and the architecture is actually what we need in order to integrate things in robotics, to integrate perception, action planning, learning, but also control. I believe that representations are key. Before thinking about how to draw the boxes of an architecture, we have to think about how to represent things in an architecture. And in particular, in robotics, in cognitive robotics or AI-enabled robotics, such a cognitive architecture must be able to process both symbolic and subsymbolic information. And what I'm going to talk about are implementations of an architecture used on the Armar robots, which have been proposed in several projects where we are continuously extending this architecture. For example, we started in the collaborative research project on humanoid robotics with the first blueprint of the architecture, and continued this work in several European projects such as the Paco Plus experience and second-hand projects. And the architecture is actually straightforward. If you draw it here, it's a classical one, you would say. It's 3 layers, but as I mentioned, the architecture is not the way how we draw these boxes, but it's about the processes and about the representations. But just to structure the discussion here, 3 layers, as I mentioned: a high-level layer for planning and reasoning, where components like natural language understanding, reasoning, and symbolic planning, or replacement strategies of missing objects, actions, or of common locations of objects, which in a plan, but also a plan execution monitor. The lower level is actually implementation or implements the robot skills. So really the robot programs which should be executed. And here we have generic representations of robot skills implemented in hierarchical state charts and a hardware abstraction layer, which allow us to abstract, of course, to the hardware, but also to bridge this architecture or these representations here to other robot middleware. And what we did in the past here, the bridge to YARP, but also recently working on bridging this architecture to ROS. The most important layer for me is actually this mid layer, yeah, which I call, or we call, memory X, which is the mediator between sensory motor data and symbolic knowledge. And as we know, this is crucial in robotics and in AI, how to generate symbolic representations from sensory motor data and how to map symbolic representation to sensory motor data or to control commands which can be executed by the robot. And we have been working on the implementation of this architecture with its different types. So where we distinguish between prior knowledge memory, in which we store everything we know about the world, like object models, environment models, robot models, working memory, of course, which give us the current state of the world, what's there, and a long-term memory in which, of course, we store things which are learned from experience and learned from interaction, where we distinguish also here between different types of this long-term memory, and in particular an episodic memory, which I'm going to explain briefly. With that here, we were able to implement complex tasks, as you see here. Prepare the dinner for 2 people with a human, where the robot knows its own abilities. So the actions or the skills it can execute, those it cannot execute, and which should be done by the human. But in particular, actually replacement strategies about entities required in a plan but not available in the current working memory. For example, here, searching for the salad bowl, where the salad bowl known by the robot does not exist or is not available, and therefore the robot has to infer based, for example, on visual affordances, yeah, that this object in the scene might fulfill the same functionality of preparing the salad. So we call that a replacement strategy. This is the replacement manager, as you see here on the top level, where this mixing bowl is taken as the object needed in order to execute the task. Of course, many of these plans or sub-plans which are generated are generated based on interaction between the human and the robot. So for example, the robot doesn't know where the corn is, and the human would tell or is telling the robot the corn is in the fridge. You see here another example for action replacements where the robot, you see here another example for action execution for the wiping, but also more complex tasks like bimanual manipulation and pushing of objects. And another example for a replacement of another object. Katya is asking for a Coke, and the robot knows that we don't have Coke at home, but based on text corpora and text mining, we build up lookup tables which tell us something like Coke, soda is a drink, and juice is also a drink, and cup is a container. And based on this information, the robot is able to replace Coke with a multivitamin juice and to serve it to Katya. As I mentioned, the second... The second example is actually building such a robot which is able to recognize the need of help of a person, of a technician in repair and maintenance tasks here. And if you think about it, it's a very difficult task also for us humans to recognize that a partner is in need of help. And you know that we can do that, of course, based on our understanding of the task, for example, lowering the guard. This is a task which requires 2 people. And if there is only one single person, then the robot should infer actually, or should offer help. But also based on haptics or force information in collaborative manipulations of heavy objects, or based on direct speech instructions. Please help me to carry this object, or please bring me the spray bottle. And in this context, we were able to implement a wide range of complex tasks. I'm sorry. A wide range of complex tasks, like removing the guard from a conveyor belt, bringing a tool, like returning the tool from the human to the robot, where of course the recognition of the intention of the human should be where the robot should recognize the intention of the human and act accordingly. But also tasks like inserting the guard, where complex bimanual manipulation tasks and compliant bimanual manipulation tasks are executed here in order to collaboratively pick up or lift this guard, transport it, and insert it in the right position. So, and what's behind that? Actually, behind that is more or less nothing else than the same architecture. Yeah, you see here these 3 layers, which I introduced previously. Of course, the low layer, the low level responsible for real-time control, the high level for all symbolic stuff and natural language processing. But what's very important here in the context of recognition of the need of the human, of course, the information about the human, where you see here the working memory. It's not only the object, the positions and configurations of the objects on the table, but also the pose of the human. And based on this world state, of course, we generate, we can coordinate the task execution. And there are other few arrows, as you see here in this diagram. These are signals which trigger actually the recognition of need of help, like based on the speech command, like based on the current interpretation of the scene. This is a very important information which should be made available for the symbolic planning in order to generate appropriate plans. But also the important arrows here, which trigger, for example, the execution of certain skills here, or the adaptation of the scene, yeah, the adaptation of the working memory and the scene representation in order to monitor the execution and to replan. Yeah, and as you see here, the long-term memory is, as I mentioned before, is the memory part actually where knowledge is coming from learning processes, yeah, from learning processes based on sensorimotor information coming from the working memory. So recently we are working on extending this long-term memory by an episodic memory, which is key for cognitive robotics. And the question is how to encode experience, how to recall the experience at the right time, not only just to recall it, but also in order to make predictions based on this experience, based on previous episodes, to predict what are potential next actions which can be executed in these situations. Another important topic we are addressing actually in our development of episodic memory is to verbalize robot experience, yeah? To have a robot which can tell you something about its own experience, what it did when it loaded the dishwasher, what happened when it grasped the red cup, and so on. And therefore, we started actually with a deep episodic memory. This means episodic memory implemented using deep neural network, where you have a video frame sequence which is fed to an encoder, which generate a latent representation of the data of the video frames, video streams. This means this encoder actually maps sequences of videos into a latent vector space. And here we use 5 convolutional LSTMs and normal convolutional layers in alternating order, followed by a fully connected layer and fully connected LSTM. And the hidden representation, this hidden representation of the last LSTM unit are, so the hidden and cell state of the last LSTM unit are concatenated. In addition, we use 2 decoders, we use 2 decoder networks with inverse structure of the encoder. On the top here, you see a decoder to reconstruct the frames that were originally given to the encoder, and on the bottom, a decoder which predicts future frames. So, and these 2 recorders, of course, operate only on this latent representation of the video stream or the video sequence fed into the encoder network. So what can we do with that? The goal is, of course, to store this previous experience in a latent space. So the goal is to have latent representations of previous experience and to store them in a database and to form such episodic memory. So this means ARMA is observing a scene. The video frames are fed. The video frames from the camera are fed through the encoder. So they are mapped into the latent vector space. And we build a database with latent representations of visual experience from the past. And to retrieve the similar experience, we search for the closest vector in the latent space to retrieve the best match. For example, here with cosine distance matrix. And based on that, we can, of course, with the reconstruction encoder, reconstruct the episode from the latent representation using the before mentioned decoder network. And you see here an example how we use this episodic memory in order to perform time-aware planning. Imagine you have the task to perform you have the task to prepare breakfast in 5 minutes, and of course in these situations you have maybe to accelerate the execution of some tasks, to skip some parts in the task, and so on. And what we do here, and the most important thing, is actually the recall of similar experience here. As you saw in the video, let me play it again. The robot is watching or observing the human performing something, and based on the previous on the recalled experience here, the robot understands that we need the pan, and maybe the robot can now start preparing the pan by pouring oil into the pan. And at the same time, as I mentioned, the generated plans here, the generated plans consider temporal constraints. This means which actions should be accelerated how much in order to fulfill a given time limit for the task. And in doing that, of course, very delicate actions like grasping are performed at the same speed, but navigating or moving from place A to B are tasks which are executed, which are sped up in the execution. I believe this is crucial, these episodic memories for robots, for a cognitive architecture of a robot, for any assistant robot actually, which should interact with the human. And in this example, we are only using visual experience, visual action experience. And recently, we extended this work by combining subsymbolic information like visual information, like speech information, with symbolic information about what's actually what's in the scene. So including, of course, the timestamp, which state of the word at which timestamp do we have, symbolic task and the actions, the object IDs and their locations, the pose and the configuration, the entire configuration of the robot, but also the images. And also with deep neural network, we learn an episodic memory verbalization model. So a model which should be able actually to verbalize robot experience based on queries made in natural language, and of course to externalize this robot experience in natural language. This is why we call it verbalization of robot experience. Here, an example.
Hey, Arma, I will be away for a few moments. Can you please tidy up while I'm away?
All right.
So now the robot will execute actually the task, clean the table, and you see here all this experience or data is stored, the robot configuration, the position, the joint configurations of the robot, the positions of the objects, of course, the IDs of the objects, the camera images of the robot. These are continuously stored as part or used in order to build this episodic memory model. And after finishing the execution, you will see that the human will come back and start actually interaction with the robot and asking the robot about what it did. I'm not going to explain the details. I'm happy to discuss that with you.
Hi, I'm back. Tell me what you did, please.
I moved the multivitamin juice to the countertop.
How long did it take to grasp the green cup today in the afternoon?
It took about 1 minute.
Tell me which object you moved to the countertop yesterday at 2 p.m.
I moved the red cup.
When did you last see the red cup?
I saw it on December 9th at 14:56.
Thank you.
So, of course, this is exciting. And as you see, the robot can give more precise information as we can do humans, that we move the cup at 2 p.m., 9 p.m., whatever. I'm not sure whether this is really needed, but just for fun, I'm showing that. So all this work actually is implemented. So I'm not really just presenting things which are working on papers and described in some of our papers, but they are implemented in our framework in ArmarX, which is event-driven and component-based software development environment for robotics in particular, actually. And on the other hand, it's a architecture, actually, because it defines all blocks which are needed and the processes and the communication between these different blocks in the different layers of this architecture. It supports the development of software for robotics from real-time control to symbolic planning, and also supports graphical programming of reusable skills with the formulation, modified formulation of the state chart. And it provides also robot-independent components like the classical stuff, motion planning, grasp planning, inverse kinematic, pose, object pose estimation. And in particular, actually, it provides a robot memory system. And I showed few examples about the recent developments regarding the episodic memory. It's open source and available for everybody, and would be happy to discuss with any of you. And of course, happy regarding any feedback on our framework. What were the key design principles of the architecture? The first thing was actually the state disclosure. So to have a consistent consistent state disclosure, this means monitoring of sensory data, events, conditions, and execution state on all levels of this architecture. The second one was actually to make robot programming on high level more intuitive and flexible. This is what we did with state charts, graphical programming framework with access to the different parts on C++ level, and where we can reuse robot skills through parameter profiles. Of course, it provides abstraction of access to robot hardware, in particular to different robot platforms, what we have here, but also to other robots, like, for example, the iCub robot, what we did in the experience project, like the Panda robot or the U-bot. And the fourth design principle was distributed, being able to distribute the execution of different parts to different PCs, and of course to ensure communication between the different components via well-defined interfaces. The software is publicly available, and here are the different packages what you need in order to start actually working with that. So the core, the API with generic interfaces for common sensors, actors, and components, configurable robot components, plug-in based GUI, the memory X. Not everything what I presented today is available, but this will be available soon, and Vision X as the most important perception component, and the robot skills, the generic robot state charts, like for grasping, for lifting, for cleaning, removing the guard, for example, transporting a box, and so on. Also a dynamic simulation and documentation. So with that, I would like to conclude with some thoughts about robot cognitive architectures. And from my point of view, there are 4 key processes which we have to take into account when developing a robot cognitive architecture. Of course, we have to take a lot of inspiration about what's known in cognitive science and in the areas where people are really investigating how cognitive information processing is working in human. But by the end of the day, we need something which is functional, which is working on a robot. And this is maybe a very key and fundamental requirements. But let me briefly talk about the key processes from my point of view for cognitive robot architecture. The first one is actually the ability to categorize perception action dependencies as non-symbolic object action effect representations. This is very, very important because based on these categorization, we can bootstrap knowledge extension in a system. So by generative modeling and symbolic representation. So generative modeling and symbolic representation to bootstrap generalized and transferable symbolic knowledge of these perception action associations and dependencies. This means the know-how of the robot about the world, about the task, from specific perception action contingencies of objects, associated actions, and consequent effects. The third key process is internal simulation. Internal simulation to be able to predict the outcome of actions or plan actions to achieve desired outcomes. And the last part is the grounding, the active grounding, to validate the results of internal simulation by observing the actual result and either reinforcing or weakening the generative model that produced these internal simulation results. These are things which we actually worked on in a European project together with many leading European researchers like David Vernon, like Giorgio Metta, Justus Pieter, Florentin Vogata, Mark Steedman, Chris Geib, and many other. These are people from developmental robotics, but also from knowledge-based robotics or knowledge-based AI and natural language understanding. And we came up with this experience cognitive architecture. Of course, it's drawn now in a different way because it emphasizes the processes which are needed in the definition of a cognitive architecture. So, and the idea is, of course, that that a robot will execute goal-directed motivated actions as sequence of motor commands on the basis of multimodal sense data. These actions and their effects on objects, together with perceptual representations of objects, are categorized and represented as affordances. We call them actually object-action complexes. These are nothing than action-object-effect triples, yeah? And ensembles of these non-symbolic oaks, yeah, non-symbolic representation, are then used or should be then used in a generative modeling process to generalize these specific instances of perception action dependencies, forming symbolic structural network of perception action associations. These models can then be used in an internal simulation to predict the outcome of actions or plan actions to achieve desired outcomes. And of course, these outcomes, which are only predictions, are subjected to validation by observation when the actions are executed. So with that, I would like actually to conclude. Here are some of the publications related to the ArmarX framework or to the ArmarX cognitive architecture. If you are interested, I'm happy to discuss details in the different sessions of the workshop. And I would like to thank, of course, our funding agencies here for the support, and thank you for your attention. Thank you.